Hi, I'm Han Shen from Huazhong University of Science and Technology. This is TextPecker, a joint work with ByteDance. I'll move quickly, so please feel free to pause me anytime. Here is our brief roadmap. I'll take you from the core bottleneck in current text rendering to our TextPecker framework and finally show you our results. Let's start with visual text rendering. It has evolved. It's no longer just a niche glyph injection task. In the LLM era, it is a foundational capability for unified generative architectures. But here is the real bottleneck. Look at today's best models: Flux, Qwen Image, Nano Banana Pro, and Seedream 4. Despite their power, they all output distorted strokes and misaligned characters, especially in Chinese. This completely blocks production use in graphic design. Why hasn't post-training fixed this? Because the evaluators driving RL are structurally blind. They suffer from hallucination, auto-correcting broken glyphs, and invisibility, skipping distorted regions. This creates a vicious loop of noisy rewards. Our insight is that the bottleneck isn't generator capacity, but this reward blindness. So our goal is to build a structure-aware evaluator and a plug-and-play RL strategy to break the loop. Introducing TextPecker. It rests on two core innovations. First, a structure-aware extractor that replaces blind OCR by explicitly flagging flawed characters with a marker. Second, the composite reward. It is split into two axes. The semantic alignment score uses Hungarian matching and normalized edit distance to handle out-of-order rendering. More importantly, the structural quality score introduces an amplification factor, because in graphic design, even one defective character ruins the visual quality. Together, they shift the optimization from coarse semantics to fine-grained structural fidelity. To train this, we faced a massive data gap. There were no character-level anomaly datasets, and Chinese makes this exponentially harder with over 8,000 characters. So we built our own. We collected real generations from SOTA models with human annotations and augmented them with a self-developed synthetic data engine to systematically inject structural corruptions like deletion and swapping. Through these pipelines, we constructed the domain's very first 1.4 million sample dataset, specifically designed for anomalous text recognition. We then fine-tuned models like QN3VL and INTERNVL3 to output standardized JSON via rule-based scoring, supporting both image-level and box-level tasks. The perception results are stark. Existing OCR and MLLMs like GPT-5 completely collapse, scoring below 0.23 F1 because they guess semantics instead of verifying structure. TextPecker outperforms them all across the board. But the ultimate test is generation. We plugged TextPecker into Flow GRPO. The gains are massive. Flux point 1 jumps 30 to 40 points, and the heavily optimized Qwen image sets a new SOTA. Blurriness, misalignment, and distortion in dense text simply disappear. Ablation studies confirm our design. Our synthetic data augmentation is crucial for restoring standard recognition, while our semantic and structural quality rewards provide independent additive gains. TextPecker also demonstrates robust zero-shot generalization on unseen models like Nano Banana. Distinguishing extreme artistic stylization from actual structural errors, however, remains an open challenge. Furthermore, TextPecker stacks seamlessly with aesthetic rewards like PicScore, achieving simultaneous improvements in both text fidelity and visual quality. To conclude, we leave you with three takeaways. First, our core finding. The true bottleneck in text rendering is the structural blindness of evaluators. Second, the framework. TextPecker revolutionizes this with a plug-and-play, structure-aware reward. And third, the results. It works with any generator, delivering consistent cross-model gains and setting a new SOTA. Our code, models, dataset, and paper are fully open-sourced. Thank you. Feel free to contact for any questions.